All right, welcome to chapter 3.4. I'm recording this from home with a little bit less equipment, so we will see how it goes. Chapter 3.4 is really focused on applications of differentials. We're going to talk quite a bit about velocity as a rate of change. And we'll get into more details in just a minute. But if you think about velocity is how fast you're going, well, how fast you're going is a rate of change. So there's a couple things we need to remember, a couple of definitions. First off is the difference quotient. Oh my gosh, my handwriting is horrendous in these videos because of the way I'm using the laptop, but we'll try to adjust. So if we look at the difference quotient as this, and you've seen this before a lot, and of course the derivative is the limit as h goes to 0 of this, but we can think of difference quotient as an average rate of change. It's an average rate of change over the interval h. So we're starting at x, and we're going to x plus h, and we're taking the y value, changing y values over the change in x values. So the instantaneous rate of change, then of course, is the limit as h goes to 0 of that difference quotient. So this is terminology that you really need to know. You need to know what the difference quotient is. You need to understand that it's an average rate of change. You need to understand the idea of an instantaneous rate of change. And just by the way, to make things a little bit more confusing, if you hear the words rate of change in calculus, the implication is automatically instantaneous rate of change. If an average rate of change is being asked for, it will say, find the average rate of change. All right, let's very quickly see if we can squeeze an example into a 5-minute video. Example 1, enlarging circles. And what we know is that the area of the circle is pi r squared. And the question is, we want to find the rate of change of the area with respect to radius. WRT with respect to. And this is a useful calculation because if you think of tree rings, the area grows at a constant rate. But because the radius is getting bigger, the rings get narrower, if you've ever looked at a cross-section of a tree. So we want to know the rate of change of area with respect to radius. And we could play around with the math a little bit. The constant rule says that we can just bring the pi part out. The power rule says that we can just take n times r to the n minus 1. So the rate of change of area with respect to time is 2 pi r. And so what would we do with that? If radius is 5, then the area is changing at 10 pi. And now this is where it gets a bit interesting, is think about units. Rate of change of area, square inches, if this is all in inches, per rate of change of radius, square inches per inch. You do not simplify to inches because this is area, which is changing in terms of inches squared, and this is radius, which is changing in terms of inches. And of course, we could also see that if the radius was 10 inches, the rate of change of area with respect to radius would be, instead of 10, it would be 2 times 10, it would be 20 pi inches squared per inch. Okay, so we'll look at